back into parametric equations in section 6 of chapter 10. And in the previous video we were looking at how to find the rectangular form of our curve, the equation of our curve, from the parametric equations. Now we're going to reverse this. We're going to be given the rectangular form of the equation of the curve, and we're going to write parametric equations that will define it. Now it's not a unique answer. You can have more than one type of answer. It's kind of how what you do to set up the initial value for x. So in this case it says write parametric equations for the curve defined by it's just the line y equals 2x minus 3 with the given definition for x. The easiest definition when you're setting up parametrics is answer A here, and that is let x equal t. So then we just substitute right into the y equals 2 times t minus 3, and there would be our set of parametric equations. Now if we wanted to make it a little bit more challenging, we pick something other than just t, and in this example b here, I'm going to have x is equal to negative 4t, so that when I go to now substitute this in for x in the equation y equals 2x minus 3, I get 2 times negative 4t, parenthesis, minus 3, which would give me y equals negative 8t minus 3. And this guy here and this guy here would be my parametric equations. Okay, I'm just going to kind of cross this out so I can put a nice brace there. For part C here, very similar. I do have a fraction, but that's about the only difference. I'm going to go ahead and substitute, first letting x be defined as t over 5, and then making the substitution. I'll do it over here. Y equals 2 times t over 5 as my x value minus 3. So this would be 2/5 t minus 3. So my second parametric equation would be y equals 2/5 t minus 3. Now if you take any one of these three sets of parametric equations and you eliminate the parameter, you're going to get right back to here. So you say, well, what's the difference? The difference is the timing. If t is representing time, they're at different locations on this line at different times because of the way x is defined. So you would just have them moving at different paces, and they'd be at different positions, but they would be on the same line. All right, now, anytime you learn a new topic, right around the corner are some applications. And so one of the, where parametric equations really prove to be useful and kind of like where they shine is when we're using them to model motion. And again, that's one of the reasons why we like to use t as the parameter, because it represents the time. So I have a nice little explanation of how to use parametric equations to define uniform linear time and projectile time. Those are the two main types that we'll look at in this section. So we let t be greater than or equal to 0 represent the time under which an object is in motion along a plane curve. And we let x sub 0, y sub 0 represent the initial position of the object when t is 0, at time t equals 0. So uniform linear motion, and you can see we have these two parametric equations. T is our parameter again, and x sub 0 and y sub 0, as we were just talking about, that's our initial placement. And then the a and the b here are going to be kind of what tells us how fast things are moving along. The a and the b are going to represent the horizontal and the vertical parts of the velocity, or components of the velocity. So I like to think of the vector AB kind of being like along the lines of like what we call a velocity vector. And that's how we're going to break this apart. Now down here we have projectile motion, like if, a cannon shoots a cannonball up into the air at a particular angle. And we use these guys here where x is equal to v sub 0, cosine of theta, t, all that times t, plus x sub 0. Now remember, x sub 0, y sub 0, that's our initial position, our initial place. And then in this case, y is equal to 1/2 gt squared plus v sub 0 times the sine of theta, t, times, plus y sub 0. Now this guy should look a little bit familiar to you, because that looks like what we have for a free-falling object, where g is gravity. Now because they put the negative here, g is actually, we're going to be thinking of the absolute value of g, because g is negative. It's the acceleration and that's considered negative because it pulls it down, but we're going to think of g for the gravity being 32 feet per second or 9.8 meters per second based on our units. That's why they put the half there. They really didn't need to do that. They could have gotten rid of the 1/2, and then we could think of that as negative amounts. And of course, theta is the angle of the way you've got this thing set up where you're kicking a football off of a tee. It's what the book calls the angle of launch, okay, relative to the horizontal. And v sub 0, you all know that's your initial speed. Now, we use initial speed here because, now remember, speed is the absolute value of velocity. And because we're looking at projectile motion, we're looking at our initial velocity that the object is going upward before it arcs and comes back down. So we're thinking of that as a positive amount. All right, and of course we're neglecting air resistance. So it's not quite exactly the fly and the spider question, but we have one here with an ant. And the example says an ant walks across a 72-inch by 30-inch picnic table along a straight line. So we're going to be using uniform, here let me underline that, uniform linear motion as compared to projectile motion because he's moving along a straight line. The origin of the rectangular coordinate system is placed at the lower left corner of the picnic table. So if this helps, I'm going to draw a picnic table here, at least from the top view of it. And this is 72 inches by 36 inches. 72 inches by 36 inches. And we are going to put the ant here at the, oh actually, hang on a second. I think to fit the way the problem is being described here, I think I'd be better off writing it like this and having the picnic table look like this, where this is 72 and this is 36 here. So it's 6 feet by 3 feet. Now we're going to put this so that the lower left corner is at the origin. Alright, so here are my axes. I'm going to make them dotted. So there's the origin right there. This point here would be the point 72, 0. This point up here would be the point 72, 36. This point up here would be 0, 36. So you've got an ant that is walking from the point 72, 10. So maybe about here. Here's the ant. And he is walking to a point at 20, 36. So 2036 might be up here. So he is walking, let's see, I have a straight edge here. Up like that. He's going from this point right here to, well, I'll just call it E for edge there, of the edge of the table. And he's going this way. So now what we're going to do here is if the ant walks from point A, I think I called it E, but I think I better call it B to match the problem, to point B in 13 seconds. Alright, so 13 seconds to go that distance. We can figure out his velocity here, but we're going to figure it out horizontally and vertically. Okay, we're going to write parametric equations to represent the ant's path as a function of time t in seconds. So we're going to assume that the distance, which they like to use S for distance in the figure, are in inches. So x is equal to x sub 0 plus at. So x is equal to, well, my x sub 0 is where he's starting at here. And he's starting at an x value of, he's starting at an x value of 72. So this is 72, that's my x sub 0. Plus, now I have to figure out his horizontal rate of speed. Now his horizontal rate of speed, since he's going from 72 to 20, I'm going to find that rate of speed here. Let me get rid of this just a little bit. I am going to find A by taking 20 minus 72, and this is going to be spread out over 13 seconds. So this is the change in time, the change in distance over the change in time. This is negative 52 divided by 13. This is negative 4. And that kind of makes sense that it's negative because I'm going to the left horizontally kind of left and up, but I'm doing it on the diagonal. So it makes sense that A is negative, so because it's negative, I'm going to write minus 4t. Now y, which is y sub 0 plus bt, y is starting at a initial placement vertically of 10, and it's going up, so this should be positive here, and we're going to go from 36 up to, let's see, hang on a second, I almost messed that up. No, I didn't. We're going to go from 36 up to 10 here, so B is equal to 36 minus 10. Yes, 36 minus 10, where he ends up minus where he started from, just like a vector, tip minus tail. And that's also divided by the amount of time it took, 13 seconds. So this is 26 over 13, which is a positive 2. So this would be plus 2t here, and those would be my parametric equations to describe this. Notice here, initial placement and my velocity here, horizontal and vertical components of my velocity. Then it says, let's see, determine the ant's location 8 seconds after leaving point A. Well, it took 13 seconds to go from here to here, so he's probably about there somewhere. So let's see if we can figure that out. Well, to get the position, since we know t is 8, I'm going to substitute into both of my parametric equations so I can figure out where he's at horizontally, x-wise, and where he's vertically, y-wise. So I'm going to plug 8 in here for t and in here for t. I get 72 minus 4 times 8 is 72 minus 32 is 40. And y would be 10 plus 2 times 8, which would be 10 plus 16, or 26. So he's at the point, the ant's location at t equals 8 seconds is 4026. So that's where he's at. I don't know if I approximated that right. That could be about 4026. Yeah, that's not terrible. If you use graph paper, you can come up with a better sketch, and that'd be a good way to check your work as well. So that's an example of using linear motion. We probably need to consider an example of projectile motion as well.